down a little bit. Okay, now the microphone's in a good spot. Alright, good morning. Today we're going to be doing Advent of Code, day 14. Every day, Eric Wastl releases 2 programming puzzles as part of the month-long challenge known as Advent of Code. So we're going to be doing this every day up until December. I'm going to be making video solutions, so hopefully this helps. The code for all my solutions is going to be in a GitHub repository linked in the description, and a playlist to all past and future videos is going to be linked in the description as well. So today we're just going to be doing day 14. I'll be doing the problems and explaining the solutions. Alright, day 14, docking data. As your ferry approaches the seaport, the captain asks you for your help again. The computer system that runs this port isn't compatible with the docking program on the ferry, so the docking parameters aren't being correctly initialized in the docking program's memory. After a brief inspection, you discover that the seaport's computer system uses a strange bit mask system in its initialization program. Okay, so first, bit masks are kind of helpful to know about, I guess. So I'll put a link to some resources in the description. So maybe you should learn a little bit about that before you do the problem, or I'm going to be using this in my solution as well because it's part of the problem. So although you don't have the correct decoder chip handy, you can emulate it in software. The initialization program, your puzzle input, can either update the bitmask or write a value to memory. Values and memory addresses are both 36-bit unsigned integers. For example, ignoring bitmasks for a moment, a line like mem8 equals 11 would write the value 11 to memory address 8. The bitmask is always given as a string of 36 bits, written with the most significant bit representing 2 to the 35 on the left and the least significant bit, 2 to 0, that is the ones bit, on the right. The current bitmask is applied to values immediately before they are written to memory. A 0 or a 1 overwrites the corresponding bit in the value, while an X leaves the bit in the value unchanged. For example, consider the following program. So they have a mask, and then they do some memory stuff. This program starts by specifying a bit mask. The mask it specifies will overwrite 2 bits in every written value. The 2's bit is overwritten with 0, and the 64's bit is overwritten with 1. The program then attempts to write the value 11 to memory address 8. By expanding everything out to individual bits, the mask is applied as follows. So we see that the 64's bit is turned into a 1, and the 2's bit is turned into a 0. So then it just gives the same example. A few more examples. Okay. To initialize your ferry's docking program, you need the sum of all values left in memory after the initialization program completes. The entire 36 address space begins initialized to the value 0 at every address. In the above example, only 2 values in memory are not 0. 1 and 1 at address 7 and 64 at address 8, producing a sum of 165. Execute the initialization program. What is the sum of all values left in memory after it completes? Okay, so this problem is pretty simple. We just sort of need to do some more emulation. And the bitmask stuff, that shouldn't be too difficult either. So I'm just going to do the problem in 5 seconds, and then I'll explain it. Okay, so we got some big value, and this is probably incorrect, but let's just see if it's right. Hey, it's the right answer. Okay, so I'll explain how we got this answer. Okay, so first of all, the input isn't too large, so we can afford to do a little bit of inefficiency. So it's only at 500, so it's not that big. We can cut some slack. So the idea here is basically just to run the program. But yeah, basically what we need to do, we just need to set masks when we are told to, and then we need to set addresses when we are told to. But before we set the address, we also want to apply the mask to the value. So here's how we do it. I wrote this function just to basically run the program. The program is just like the input, basically, but it's a list instead of just the raw string to make it a little bit easier. So we initialize the memory, and the memory we can't just make it a huge array, because as we can see, the input numbers are a little bit big. So we're going to make it a dictionary, but we're going to make it a collections.defaultDict. And this basically just initializes all values to 0. And then as we input values, it calls them. And if we don't initialize any values, the default value will be 0. So we can still call memory 0 and it will be 0, even if we haven't initialized it yet. And we can't do this with regular dictionaries. and this is the equivalent of a map in other languages. So we just initialize our memory, and then we initialize our mask. We don't actually need to do this, but it just yeah, we don't actually need this, but it makes the ID a little bit bad. Actually, no, it doesn't. Okay, so then we go through every line in the program, and every line is just like one line in the input. For every line, we split it up by spaces just to make it easier to parse, because we need to do this anyway for whether it's whether it's a mask, setting the mask line, or it's setting the memory line. So we just split it up into parts because that's necessary. If it's a memory line, then what we need to do, we need to find the address, which is pretty simple. We just need to find what's between these square brackets, and we turn that into an integer. So we just have the address stored, for later. And then our value is just what's in what's on the right half, right? So we just get our value. We convert that into a string. So that's what this bin value to colon means. So if I type into the interpreter, for example, bin 42, I will get 0b101010 as a string. And this is just something in Python. I know I could do more efficient bitwise operations using like actual bit masks and stuff, but I just wanted to make this easy to explain, and it runs fine because the input isn't that large anyway. So it's a little bit easier to understand. If you came here to understand bitwise operations, my apologies. Maybe I should do that. Maybe that's going to be in part 2. Who knows? But resources are always in the description. Maybe I'll make a video on bitwise operations in the future, which includes this problem. Okay. So we just turn this into a list of bits. So for example, why don't we just print it out? Print bits. And then if we run our program, we see that it's just a list of single characters, and each character is either 0 or 1. So that's our array of bits, or list of bits. Then we need to apply the bit mask. So the mask is just a string of 36 characters. The array is also 36 characters long. So for every character in the mask, if it's not an X, then we need to set that bit in the array. After that, we convert our new array with the flipped bits as necessary. We turn that into one long string, and then we convert it back into an integer. So for example, if we type into the interpreter int 101010 and then add 2 as an argument, it will interpret it. Turn that into a base 2 number, so it'll turn that into 42. So what we do, that's what we do here. We just convert that big array of characters into one long string, and then turn that into an integer, base 2, interpreted in base 2, and then we have our new modified memory value. So that's what this thing wants us to do. Over here. Okay, and then otherwise that's just for the memory lines. If it's a mask line, then we just need to set our mask variable. Okay, after that we have our default dict, and then we return that, just to make this function more reusable, After that we just take a program, we run it, get our dictionary. After that, we sum every key in the dictionary because the default value is 0, right? So we just need to sum every key that we have touched. We sum all those, and then we get an answer. So that's pretty simple. All right, moving on to part 2. For some reason, the Cport's computer system still can't communicate with your Fairy's docking program. It must be using version 2 of the decoder chip. A version 2 decoder chip doesn't modify the values being written at all. Instead, it acts as a memory address decoder. Immediately before a value is written to memory, each bit in the bit mask modifies the corresponding bit of the destination memory address in the following way. If the bit mask bit is 0, the corresponding memory address bit is unchanged. If the bit mask bit is 1, the corresponding memory address bit is overwritten with 1. If the bitmask bit is X, the corresponding memory address bit is floating. A floating bit is not connected to anything and instead fluctuates unpredictably. In practice, this means that the floating bits will take on all possible values, potentially causing many memory addresses to be written all at once. Okay, that's very interesting. For example, consider the following program. Okay, so it sets memory at 42 to 100, and then 26 to 1 with different masks. When this program goes to write to memory address 42, it first applies a bit mask. Okay, so this gets turned into X, that gets turned into X. After applying the mask, 4 bits are overwritten, 3 of which are different, and 2 of which are floating. With 2 floating bits, 4 actual memory addresses are written. Okay, that's very interesting. Next, the program is about to write to memory address 26 with a different bit mask. Okay. This results in an address with 3 floating bits, causing writes to 8 memory addresses. The entire 36-bit address space still begins initialized to the value 0 at every address, and you still need to find the sum of all values left in the memory at the end of the program. In this example, the sum is 208. Execute the initialization program using an emulator for version 2 for a version 2 decoder chip. What is the sum of all values left in memory after it completes? Okay, this is going to be slightly difficult because we can't just brute force this, but I'll find a way. What, can we brute force this? Wait a minute. Okay, so stay with me here. I'm gonna print out how many X's there are. Count equals 0. Okay, you know what? Yeah, stay with me. So this might not actually be that bad. So yeah, so we can see that there's only like a few values of X's here. So this can't be that bad. All right, let's get to it. Okay, so we got our answer, which is very big, and let's see if it works. It's gonna be difficult to explain. All right. Yes. Okay, that's right. So let's explain this. This is gonna be more difficult. Okay. Okay. So the idea here is that we're going to need to actually just brute force this. So maybe I should do some diagrams. So I'll do that. So we are basically doing the same thing this time, except we're modifying the address instead of modifying the value. And it uses kind of the same scheme, except it's a little bit different this time. And actually it's quite a lot different. So this time we convert the address into a list of characters instead, the list of bits instead of the value. Because we need to do all possible addresses, right? And we need to modify the address. So we have the same loop, which goes through every single bit in the mask. In the mask, if it's a 1 or an X, we want to set that bit in the bits array to be the same as the one in the mask. Because here, let's do an example. All right, so let's suppose the mask is like, and let's just assume it's not 36 for now. Let's say the mask is something like 10x10, right? And then our address is equal to, say, 00000. So this is the new address. We want to convert it, right? So the 10, 1 makes it stay the same, and X, we also want to put X in our new address as symbolizing floating. So X symbolizes floating. That's what I wrote in this comment over here. So if it's a 1 or an X, it just becomes that. So that's what happens here. If it's a 0, then it stays the same. So it actually becomes the same thing as the mask, which is a little bit confusing, but yeah, maybe I should do that a little bit differently, just to make it a little bit clearer, you know. Maybe I'll make this one 1 and make that one 0. So let's just make this a 1, 0. So as I said before, 1s and X's just convert themselves into the address, and then 0s in the mask make the address bit stay the same. This is our new address. And that's basically what we do over here. We also want to count how many X's there are, just for convenience's sake. So in this case, there would just be 1X. And that's what we do over here. X count just counts the number of X's. We add it by, we increment it by whether that bit is an X, because if that's true, then it's a 1, and if it's not, then that's a 0. Okay, after that, let's do a more complicated example. Let's suppose our mask was something like 0, 1, 0, X, 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 X. All right, and then our, let's say our address was something like 10, 10, 101. Okay, I'm not very creative, okay? So our new address is going to be, here, I'll just figure out my own. So yeah, they kind of said this in an example, but basically we just end up with this thing. We have 4 x's, right? And then we need to actually convert this into all possible ones, all possible new addresses. So it'll be 111, it'll start with 0000, and then it'll go 1110001, and then go 1110010, and then so on, all the way until 1111111. So this is going to have 16 possibilities, and 16 is 2 to the 4, because every single floating bit has 2 possible values, 1 or 0, and then since there are like x count of them, there are 2 to the power of x count ways to flip those bits around. In this case, x count equals 4, so there are 16 ways to flip them around. And that's why we need x count, right? We need to find how many ways there are to flip them around. And then we do permutations of 1 and 0 to get our x count. I mean, not our x count. We just to get how the floating bits should be like done, basically. In our example, x count equals 4, so this is going to return a like, I guess, list. It's not really a list, it's a generator, but it's a list of 16 possible outcomes for the bits, for the floating bits, that is. So for every single permutation of 1 and 0, we could actually do this with incrementing a counter up until 2 to the power of x count and then turning that into binary, but we're not doing that for now. We're using iter tools. That's a little bit too complicated. So for every permutation in there, we get something like, for example, 0, 1, 1, 0. Okay, this is, for example, a permutation. This is actually a list, but that's the same as a string, basically, for our purposes. We do a copy of the bits list, and this bits list, remember, it's representing the address as a list of bits. So we make a copy of that list because we don't want to mess around with like modifying what we already have. So we have a list of the bits in the address. For every for every bit in that, we want to make sure we want to change it if it's an x, right? So let's suppose this was our permutation. This is basically specifying that the first x should be a 0, the second x should be a 1, the third x should be a 1, fourth x should be a 0, and that's 1 in x. So basically what we need to do is basically that. So we just need to turn the first x into a 0, second x into a 1, so on. So let's say, for example, that our string was 111 x x x x. And this example is actually a little bit simpler because the x's aren't in the middle. Basically what we do, we keep counter of how many x's we've seen so far. It starts at 0. As we see an x, we increment it by 1, and we also change that x to the desired index. So first it starts at 0. Our x index starts at 0. We go through the first one, the second one, the third one, nothing changes. The third one is an x, so we change that to 0, and then we increment our x counter, so now it's at the first value. And the next x we see, that turns into a 1, and then we go to the next one, and that also turns into a 1, and we go to the next one, and that turns into a 0. So that's basically what we do in this for loop over here. Every time we see an x, we map it to the corresponding index in our permutation, and then we increment the x counter by 1, x index actually. And this way, we ensure that every single permutation is counted of the floating bits. And then, yeah, after that, we just turn our address back into an integer like we did in part 1. And then we assigned that value in the memory to the new value. After that, we just delete the copy to make it a little bit, to save a little space, but we don't really need that. That's a little bit extra. Yeah, and that's it for memory lines. If it's a mask, we just set it as we did before. We set the mask. And after that, we just return the dictionary as we did before, and the rest is the same. So yeah, hopefully the explanation was clear. It might have been a little bit unclear because, you know, bit masks and stuff like that. These bit manipulations are a little bit complicated. But I didn't try to do it, you know, the really professional way that saves a lot of time. I just did it, you know, it works, and that's all that matters, right? If the input was a little bit larger, it might lag, but this is all we have for now. So, you know, I figured it's fine if we don't do it the smart way. Smart way requires doing some built-in bitwise manipulation stuff. Not really built-in, but kind of built-in, like bitwise and whatnot. We could have used that, but I chose not to. I chose to make it easier to explain, made the code easier to read, and more self-explanatory, I guess. More self-explanatory. Okay, so that's basically it for day 14 of Advent of Code. Hopefully that made sense. Hopefully that helped. Looks like we're going backwards in the lines, and we'll eventually be landing at our tropical island destination, but that's it for today. We are going to be docking with the port. So yeah, that's it for day 14. Also, I'm going to ask you to please consider subscribing to my channel, because I'm trying to hit 400 subscribers by the end of the year. It really supports me. I'm going to continue to make this content in the future, like programming content. So if you enjoy it, please consider supporting and subscribing. Let's get to 400 by the end of the year. I've seen a great increase in the past month. So, you know, we're on track. We're on track. All right, so thanks for watching. As always, feedback is appreciated. Leave some in the comments or DM me on Discord. And that's basically it for day 14. So, thank you for watching, and I'll see you tomorrow at day 15.